Hi, welcome back. We're looking at difference equations and in particular how they relate to frequency response and discrete time Fourier transforms. So I've got this example here. A certain causal LTI system has the frequency response given by this thing, capital H. Find the impulse response, a difference equation that characterizes the system, and the output of the system when the input is this thing here. All right, I think we're going to need a little bit of space here, so I'm going to come to the right and solve A. So, first of all, if we have to know for A that the impulse response is the inverse transform of the frequency response. So we need to inverse transform this thing. Well, I look at my table and I don't see anything that really matches this form. I don't see a common Fourier transform pair there. So what I do know is, though, that you see this guy here, if we consider e to the minus j omega to be like x, or some variable like from calculus, then x squared is e to the minus j2 omega, right? So what I'm saying is this is actually a quadratic. The denominator is a quadratic in e to the minus j omega. This is the square term, this is the linear term, and this is the constant. That is all to say that you can factor this denominator. Maybe if the math gods allow us to do it by hand, maybe, but sometimes we need the quadratic formula. Okay, so remember, we're considering the variable to be peanut butter, jelly, and bread, omega, j, and e. They all come together. So let's consider that to be the variable x, and let's see if we can factor that thing. So I'm going to write capital H as 1 over, and then the question is, can I factor it? And it looks like the math gods will allow it, right? I can factor this as follows: 1 minus 1/2 e to the minus j omega times 1 minus 1/4 e to the minus j omega. Now, if you didn't follow this business in orange over here, what you can do is FOIL this out and then you convince yourself that you get this back. So for example, if the first is 1 times 1, there's our 1. The outside is 1 times negative 1/4 e to the minus j omega. Then the inside is negative 1/2 e to the minus j omega, which makes minus 3/4. That's this term. And then the last, here's what I was saying about the square. The last is 1/2 times 1/4, which makes positive 1/8 e to the minus j omega times e to the minus j omega. Because of exponents, you add the exponents. So we get e to the minus j2 omega, giving you the squared term there. All right, so now the idea is that if I know the factors, I can expand this. I can use partial fraction expansion to write this as two fractions, a sum of two fractions. So a and b here are constants, okay, and we have to determine what those constants are. So this is the method of partial fraction expansion, and I don't care how you learn partial fraction expansion. You can use whatever method you want as long as you can do it correctly. However, I think my method is better than your method, and I will try to persuade you to use mine. I can do this in my head, and I'm not very good at math and doing things in my head, so I bet you can do it in your head as well. What we're going to do here in the orange box is multiply everything to get A, so I'll write A colon. To get everything, I guess to get A, we're going to multiply by A's denominator and then set e to the minus j omega equal to whatever makes A's denominator 0. So let's multiply everything in orange by, that is the entire equation, by A's denominator. So on the left, or on the top I guess, we would have a factor cancel, right? Like this, equals, and then we would just have A because we multiplied by A's denominator, and then B times A's denominator over B's denominator. And then we have an equation, we still have an equation in in omega, or e to the minus j omega. So this equation must be true for all omega. And so I'm going to strategically pick a choice. I'm going to let e to the minus j omega. I'm going to strategically pick a choice. I'm going to strategically pick a value for e to the minus j omega. And I'm going to pick whatever makes this term here, whichever makes a's denominator 0. And in this case, it would be 2. Because then I'd have 1 minus 1, 0. So when I let e to the minus j omega equal 2, then this term is 0. So that wipes out the unknown b, and then I'm left with a equals 1 over 1 minus 1/4 times 2. So 1/4 times 2 is 1/2. So I've got 1/2, so I've got 2 there. So a is 2. So can we do b in our head? So multiply by b's denominator and set e to the minus j omega to be whatever makes b's denominator 0. So can we do it? Well, if I do that, I'm going to have b equals 1 over 1 minus 1/2 times 4. So feel free to pause the video and consider that if you want. But 1/2 times 4 is 2. So 1 minus 2 is negative 1. And so it looks like this is negative 1. Did we do that correctly? I think we did. Okay, so there is b. And so now we can expand our frequency response as a, 2, over 1 minus 1/2 e to the minus j omega, then plus b, so minus 1 over 1 minus 1/4 e to the minus j omega. Now how did that help us? Well, let me remind you of a common Fourier transform pair in our table. Alpha to the n u of n has Fourier transform 1 over 1 minus alpha e to the minus j omega. So I use the linearity property, so I can take this piece first, pieces separately, right? And then so I get h of n, taking the inverse transform, I can just write the 2, then I have 1 times the inverse transform of this thing, and I form fit this, and I see that alpha is 1/2, so then the inverse transform is 1/2 to the n u of n minus, then from linearity I can consider this piece, I form fit this, and I see that alpha is 1/4, so this is 1/4 to the n u of n. I could factor out the u of n if I like, but that is the impulse response of this system. So that's part A. Moving on, let's look at B, a difference equation that characterizes the system. So remember, in LTI systems, okay, we've got this impulse response, and we're putting in an x, and we're getting out a y. And for LTI systems, the output is the convolution of x with h. Now, the convolution property of Fourier transforms tells us that the convolution in time is multiplication in frequency. So I can write y capital is equal to x capital times the frequency response, right? Okay, in other words, h, the frequency response, is the ratio of y to x, right? Okay, so let's take the original h, right? So we've got 1 over 1 minus 3/4 e to the minus j omega plus 1/8 e to the minus j2 omega. There's the original capital H. And that's a ratio then of y of e j omega to x e to the j omega. So I cross multiply, and I see that x equals y minus 3/4 y times e to the minus j omega plus, I'm going to try to squeeze it in here, 1/8 y times e to the minus j2 omega. Okay, so now I take the inverse transform of that equation. So the inverse transform of capital X is lowercase x equals the inverse transform of capital Y is lowercase y. Now, and I can do this piece by piece from linearity. So now I can just consider minus 3/4. Now the inverse transform of capital Y times e to the minus j omega from the time shift property multiplying by a phasor in frequency is the equivalent of shifting in time. And so I look here and I see there's a 1 multiplying omega. So this is a shift, this is a delay by 1 unit in time. That's the inverse transform of that. And then similarly, I've got 1/8 times the inverse transform of that. I see a 2 there, so that's a delay in 2 units, like that. And that is my difference equation. So I've got part B done. Okay, so now part C, I think we're going to need a little bit of space. The output of the system when the input is this thing. Okay, so first I want to mention that you could, if you were so daring, you could convolve x with h, lowercase. Now that we have h, you could convolve them. That gives you the output. However, since we're talking about discrete time Fourier transforms, we're going to use the frequency response and Fourier transforms to get the output. Okay, so I'm going to use capital H again. So I'm going to delete all of this. Yeah. Okay. All right, so the output of the system. So remember, and I just erased it, but I hate when that happens. Remember that the output of the system is the input of the system times the frequency response. Okay, so we have the frequency response, capital H was given in the problem. Can we get capital X? Well, from that table of common Fourier transform pairs, we form fit this and we see alpha is 1/4, so this thing has Fourier transform 1 minus 1/4 e to the minus j omega, right? So we've got capital X. This is capital X. Okay, perfect. So now we take this thing times h. So I'm gonna use the original. I'm gonna use this h, factored h, and you notice then I pick up the second factor. So now when I do that multiplication, I've got this 1 over 1 minus 1/2 e to the minus j omega times 1 minus 1/4 e to the minus j omega squared, right? Because I pick up this factor when I multiply x by h. So now from partial fraction expansion, and I don't want to get into why this is, but hopefully you recall the form of the expansion is like this. I've got something over 1 minus 1/2 e to the minus j omega from this term. I have something over 1 minus 1/4 e to the minus j omega from this term, and then I have something over that repeated root, 1 minus 1/4 e to the minus j omega squared, like that. Okay, and so this is the form, and again I don't want to get into this, but this is what the mathematicians tell us. So now it turns out that I can get from my method, I have to amend my method a little bit, but I can get A and C very quickly using what I've already described. So I take A and I multiply everything by A's denominator, okay, and then I let e to the minus j omega be equal to 2 in this case. And so I get A is equal to 1 over 1 minus 1/4 times 2, all of that squared. So 1/4 times 2 is 1/2. 1 minus 1/2 is 1/2. So this is 4. A is 4. Okay, I can get C easily. Multiply everything by C's denominator. and let e to the minus j omega be 4. So I will get c equals 1 over 1 minus 1/2 times 4. And so it looks like this is going to be 1/2 times 4 is 2. 1 minus 2 is minus 1. So it looks like c is minus 1. Now I run into trouble when I try to get b. Okay, and the reason I run into trouble is this. Let me demonstrate. If I tried to use my method by multiplying everything by b's denominator and then setting e to the minus j omega equal to 4, what happens on the right, okay, is that when I multiply by b's denominator, I get one of these to be canceled, right? But still, c is divided by this thing. So when I let e to the minus j omega be 4, then I'm dividing by 0, and that's not going to work because of the repeated root. Okay, that is just not going to work. So what I'm going to do here, and this can be done quickly, just not all that is as quick, and it takes some practice. And I'm gonna show my steps. I'm gonna write it all out, but you'll see that a lot of things cancel, and you don't really need to write this out too much once you get the hang of it. But I'm gonna multiply. So I'm trying to find b, but I'm gonna multiply by the repeated root. So I'm gonna multiply everything by c's denominator, which is the repeated root. So on the left, I get all of that canceling, right? So I get that square term canceling. On the right, I have a over a's denominator, like this, times c's denominator, okay, which is this. And then for b, I get b times one of those factors, right, because the other one cancels with b's denominator. And then with c, I just get plus c. Okay, so how does that help us? Well, now I'm going to take the derivative versus the variable, and we're going to call the variable e to the minus j omega. Okay, this seems like a lot, but as you'll see, things end up canceling very nicely. So I'm going to take the derivative versus e to the minus j omega of this whole equation. So on the left, I have bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom. So the bottom, this is like the variable, so the derivative of the bottom is just negative 1/2. So this makes positive 1/2 in the numerator. Bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. So 1 minus 1/2 e to the minus j omega squared equals. Now, I'm going to take the derivative here, but you're going to see that this cancels, a lot of this cancels, but let's just do it. So the bottom, so we'll stick a there, bottom, 1 minus 1/2 e to the minus j omega, bottom, times the derivative of the top. So the 2 comes down from the chain rule. I have this. Yeah, from the chain rule, then I have a negative 1/4. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is just negative 1/2, right? All over the bottom squared. Okay. Yikes. Right? I mean, it's not hard, but it's just tedious. Okay, so that's the derivative there. And then the derivative here is, so I've got plus b times so the derivative here is negative 1/4, right? Negative 1/4. And then the derivative of c is just 0. That's a constant. Right, so that goes away. Then I let e to the minus j omega be equal to 4. Okay, I let that equal to be 4, and then you see what happens here. This is 0, this is 0. So the total contribution, then I have 0 minus 0 over something that's non-zero. The total contribution from a goes away, and so I'm left with 1 half over 1 minus 1 half times 4 squared equals minus 1/4 times b, right? And so then that makes, let's see, so I've got 1 over 2 times, so 1 half times 4 is 2. 1 half times 4 is 2. 1 minus 2 is negative 1. Squared is 1, so that's 1. So that's equal to minus 1/4 b multiplied by negative 4, and that makes b equal to negative 2, it looks like. Perfect. So now I've got the expansion, I'm running out of space, so I'm just going to fill in my constants here, a, b, and c. By the way, to summarize what we did here to get b, we multiplied by b's repeated root, which was the square, took the derivative, and then set what makes b's derivative equal to 0. Okay, so we found a to be 4, right? We found b to be minus 2, and we found c to be minus 1. Okay, so that's the output spectrum, and then we need to take the inverse transform of that. So we apply the linearity property, so I can take this term separately. So this is 4 times the inverse transform. Well, I form fit this, and I see that the inverse transform is 1 half to the n u of n. And then I look at this, and I take the negative 2 out, and then I form fit this, and I see the inverse transform is 1/4 to the n, right, u of n. And then I form fit this one, and this one is in the table as well, and we looked at it in a previous video. So I take the minus 1 out. This one actually has the transform n minus 1, or excuse me, n plus 1, 1/4 to the n u of n. So that's also in the table, okay? And we've already proven it before with one of the properties, but that's the answer to that one. That's the inverse transform of that piece. And so our final answer is right there.